an interesting issue with k-means is the number of clusters and how you determine that. So one question that you would like to answer if you don't know anything about your data is how many clusters are there? K-means cannot answer that question for you. K-means expects you to say how many clusters there are in the data. Now, you might be tempted to say, okay, we have an objective function. We know that k-means is trying to reduce intra-cluster variance. So let's see what value of k is optimal, what value of k gives you the lowest variance in the data. And the way you could do that is you could say, I'm going to set k equal to 2, run the algorithm, see what distance I'm going to get, what variance v I'm going to get. Then do it for k equals 3, k equals 4, and each time I'm going to record what is the final variance. The problem with that is, as you increase the number of clusters, the variance is going to keep decreasing. And it's going to keep decreasing the more centroids you add to the data. To quickly convince yourself of why that is the case, think of a scenario where every data instance gets its own centroid. What is the variance then? 0. And in every other case, the variance is going to be greater than 0. Because for some data point, the cluster centroid is not going to be on top of it, it's going to be somewhere else. Right? And in general, the more centroids you throw at a space, the closer a data point is going to be to its nearest centroid. So the graph is going to look like that. The variance is going to keep going down and down and down. It's annoying. You might try to temper it by a validation data set. So use train k-means on the training data and then measure the variance on the validation set. A lot of the time that bumps into the same problem, and the argument is a little bit more involved, but you might be able to convince yourself that if your training set and your validation set are representative of each other, so if they're random subsamples of the same data set, you are still more likely to have lower variance if you throw more cluster centroids into the space. So validation set is not going to help you. So what do? If you read the textbook, they actually suggest MDL, minimum description length. It's a fairly esoteric thing to do. What you do there is you say, what I'm going to do is after the clustering, I'm going to encode or I'm going to compress the data. So I'm going to have to compress the k different cluster centroids, and I'm going to encode the deltas, the differences between each centroid and the points that are assigned to it. And then we're going to look for some value of k that leads to the smallest possible description length. So it's a nice idea. It runs into a wall when you need to decide how you're going to encode real-valued vectors. And of course there, depending on the encoding strategy you get, you're going to end up with totally different optimal values of k. So it's not a good answer to the question. So how do you do it in practice? In practice, you do it visually by looking at the data. My God. So what you're going to do is you can plot this variance as a function of the number of clusters, and we said that it's going to decrease, right? So the more clusters you throw at it, the lower the variance is going to be. But it's not going to decrease uniformly. In most data sets, you're going to get a plot that looks kind of like that. So it's going to decrease quickly at first, and then it's going to decrease slower and slower and slower. That plot is often called the scree plot. So the analogy that you want to get in your head is imagine that this is a mountain, the tallest mountain that you can imagine, Arthur's Seat. And this is the mountain proper, right? And that part right there, that's the rubble. So that's the little rocks that fall off of Arthur's Seat and sort of clumped up at the bottom. So the idea there is that the mountain proper, that matters, right? And the rocks, you kind of want to ignore that. So you want to find a point where the mountain ends and the rubble begins. And how do you do that? Well, you do it visually. Right? So you look at it and you say, according to my eyes, k equals to 3 looks like a reasonable point to stop. You can try to get a little bit fancier about that. So you can say, okay, there is a way to mathematically represent that point. That's the point that is the steepest elbow, right? So if you imagine an elbow, So I'm looking for the point that gets the steepest bend, and that can be represented as a second derivative of the variance as a function of k. But in practice, all sorts of issues come up, and if you want to do it reliably, you do it visually.